Periodic trends are a direct result of the number of protons in an element, in other words, the arrangement of the periodic table by atomic number, which is also further explained by the interaction between the protons and the electrons, that idea of Coulombic attraction. This means the first thing we're going to discuss is effective nuclear charge. Effective nuclear charge is basically what an electron experiences. So it's the pull, that electrostatic force that an electron experiences towards the nucleus. It has to do with the distance, the number of electrons in between it, and the number of protons within the nucleus. In essence, it's how attracted the electron is to the nucleus. Now, how this is determined is it's based off our effective nuclear charge, which is our ZF here, is the result of the actual number of electrons, the number of protons, and the number of shielding electrons. In other words, in essence, what my core is. So these are typically my core electrons. So it's what electrons are between it and that nucleus. So when you look at the example here of sodium, sodium has our 11 protons. We have a single valence electron. That's typically the one we're going to be dealing with. And we have 10 core electrons. In other words, there are 10 electrons in filled shells and subshells between this one valence electron and this one. Remembering that sodium's electron configuration is in essence neon 3s1, 1s2, 2s2, 2p6. And that's where we get the 10 core electrons. So we have 10 electrons between this electron and the nucleus. So my effective nuclear charge is my number of protons, 11, minus the 10 core, which gives us an effective nuclear charge of 1. Now, if we look at something like beryllium, I said beryllium, I meant magnesium, but when we look at again we see our electron configuration, neon 3s2, so magnesium has 12 protons. We have the same 10 inner electrons, the same 10 core, and in fact now we even have 2 valence electrons. But my effective nuclear charge is the same thing. Now I have 12 minus 10, so now I have an effective nuclear charge of 2. In fact, when we look at all of what would be considered the main groups, the main group elements, which are basically our S and P, the column number will equal the effective nuclear charge. So column 2, effective nuclear charge of 2. When I get to column 3, where boron and aluminum are, I have an effective nuclear charge of 3, because again, I'm always going to have 3 more protons. Now, the reason we care about this is the other trends, the periodic trends that we're going to be discussing. Sizes of atoms, ionization energy, electronegativity, electron affinity. And then let me find the other ones. Okay, we have ionization energy, our electron affinity, etc. Alright, so let's go back and summarize our effective nuclear charge. So in essence, we know that electrons are attracted to the nucleus but repelled by other electrons, hence the influence of the shielding electrons in the core. We know that it is applied typically to the valence electrons, so we're looking at how this is attracted to that nucleus. And it is influenced by the same things that influence basic Coulombic attraction. The distance of that electron from the nucleus and, in essence, that amount, that charged quality that attracts the electron to the nucleus in the first place. So a quick definition when you discuss the size of an atom, it always has to do with the bonding radius. So notice this. The electrons can't get any closer because we have nuclear repulsion, we have electron attraction. All of the interaction of the electrostatic forces here is what determines the bonding length. Now that bonding length, the distance, the radius is half that distance. That's what determines the size of the atom. Now the general trend has the size of an atom increasing from top to bottom and decreasing from left to right. However, the trend alone, knowing that, is not enough because it's not the why. The why is the effective nuclear charge and the increasing value of N. In other words, I keep adding a shell of electrons. This puts each successive valence electron further and further away from the nucleus. So that increasing distance is what increases the size of the atom as we go down, and the increasing effective nuclear charge is why we see the trend to the right. The reason I make this point is if you're going to compare something like oxygen and fluorine versus, so let's say oxygen versus fluorine versus, let's say lithium versus fluorine, the size difference here is not enough to explain the observed differences in characteristics, but this is. If I'm looking at something like lithium and fluorine, again, the size difference is a little more significant. But when they're side by side, you have to go back to the cause of the trend. And you always have to deal with this in terms of the cause of the trend, as with all of them. So here's the thing. Since we know that the distance and the effective nuclear charge have an impact on the volume of the atom, because that's in essence what we're looking at here, that then we see that further complicated within ions, or expressed in ions, because ionic size literally depends on the number of electrons. And when you form an ion, so when I add an electron, I change the volume. When I remove an electron, when an electron goes away, I change the volume. So cations are always smaller, anions are always bigger. Again, this goes back to the attraction and the repulsion of electrons and protons. So the reasoning for this has a lot to do with what's going on in terms of going back to effective nuclear charge and repulsion. So as I remove an electron, I now have more protons per electron. I increase that effective nuclear charge in essence, plus there's fewer repulsions between the electron cloud. Conversely, with anions, we see less effective nuclear charge because I have more electrons per the same number of protons, and there's repulsions between the electrons, pushing them further apart. So we see a general trend. You're going to see ions increasing in size as you go down a column. Again, even though I'm removing an electron from the outermost shell, as I move down, each ion still has one shell more than the one above it. And we see a change as we go across, though. And this is what's interesting, and this is what leads us to what's known as an isoelectric series, or an isoelectronic series. If the ions have the same number of electrons, which is what we see when we look at something like lithium and beryllium compared to hydrogen now. They have the same number if we look at them in terms of helium, hydrogen, all of those. When I look at oxygen, fluorine, sodium, magnesium, aluminum, these ones here, let me highlight them. These all have the same number of electrons. They're all sitting at 10 electrons. So that's our isoelectronic series. Notice that the trend is basically that the ionic size will decrease with an increasing nuclear charge, which makes sense. So here I have 8, 9, 11, 12, 13. So you can see how we see that trend playing out as long as I have the same number of electrons. So the formation of those ions has to do with two things: ionization energy and electron affinity. Now, ionization energy is the removal of the electrons, whereas electron affinity is the addition of electrons. Both involve changes in energy. So the first step will be ionization energy. And as you can see from the definition, it's simply the amount of energy required to remove an electron. Now, one point I want to make about when we compare the first to the second. Basically, remember that when you remove an electron, there's an instantaneous reorganization of the remaining electrons, so that we have a big jump from our first ionization energy to our second ionization energy. The second ionization energy is always significantly higher than the first, and a lot of it has to do because we've reorganized the remaining electrons. What we said would happen with a cation, if I remove an electron, each successive one is going to be harder to remove because of that reorganization. It gets smaller every time I remove an electron, and that's going to impact the energy required to remove the next one. And this all goes back to that idea of Coulomb's law, where we see the charges versus the distance between them. And this has an impact because as I remove electrons, okay, that effective nuclear charge is changed, the radius changes, and so each successive electron removal is more difficult. Now, as you can see from this chart, and this is the same chart in your book, you can see how when I remove an electron, I see a huge jump with the next one, and you can see this play out all through all of the elements, not just the ones shown here. Now, a couple of points about what's shown here is pick up on what they give you as this blue line right here. That blue line represents what in essence is the quantum leap, okay, what they call the quantum leap of energy required to remove the electron when I eliminate the valence to get to the, and that's where we see this big leap. Now, general trends, you typically will only have to worry about first ionization energy. And as we saw with atomic radius, although this is the opposite, you still see a general trend of decreasing as we go down, increasing as we go across, and that ties back into Coulomb's law where we have that distance difference. And it also boils down to the distance from the nucleus, so the N, your quantum number, and the effective nuclear charge experienced. So those are the general trends. Now, there's a couple of places of exceptions, shall we say, what they term discontinuities. And the first has to do between 2 and 3A, and that's because we go from S2 and now we add a P1, and those inner S ones apply just enough repulsion to make it easier to remove that first ionization, that first electron in the P1 orbital. And then when we go from 5 to 6A, because then we go from P3 to P4, and in terms of our orbitals, we're looking at, remember, P3 is this, and then P4. So again, a little bit of repulsion helps make that a little easier to remove. Now, this is where PEZ was so important, and why we talked about PEZ earlier and why we're discussing it here, is when you look at PEZ, notice that only one of the peak in our PEZ corresponds to what we had in the chart in terms of second ionization energy. In fact, the only peak that matches is going to be the first one, right here. That's the only peak that matches. And again, it goes back to what I wrote earlier in that every time I remove an electron, there is a complete reorganization of the electrons that remain, and that influences this next one in terms of how we traditionally remove ionization, how we traditionally move electrons from atoms in the gaseous state, and that's what ionization energy is. PEZ is based on different data, and so we see what would be more than likely a more accurate energy requirement to remove successive electrons. Brings us to electron affinity. Basically, electron affinity is the opposite of ionization energy. We're adding an electron. This always releases energy. So we see a general trend again. It follows the ionization energy trend, and you can see how it generally becomes more negative. That means it's more likely to accept an electron. And those are the general trend. And again, the discontinuities follow what we saw with the electron configurations earlier on with the first ionization energy.